Today, let us discuss about energy stored in a charged capacitor. What are the basic things? A typical capacitor has the two plates. What are the two plates? One is a positive plate, we can call it, another is a negative plates. So there are the two plates in the capacitor. And both the plates are separated by some dielectric medium. Here is between the two plates, some dielectric medium is placed. What is the use of dielectric medium? Dielectric material can store electrical energy in the form of electrostatic energy. And today we are going to find out expression for energy stored in the capacitor. This is the basic circuit diagram for charging a capacitor. So we got a resistor here, we got a capacitor, we got a supply voltage, and we got a switch here. For switch for the purpose of on and off of the capacitor circuit. And before charging the capacitor, the plates of the capacitor are neutral. Neutral means both the plates, every plate, the positive plate as well as the negative plate, they have the equal amount of positive and negative charge. Therefore, before charging a capacitor, each plate of the capacitor is neutral. When we close the switch, yes, so suppose I close this switch, then what will happen? The current start flowing through the circuit, and this current flowing through the circuit is used for the charging the capacitor, and that current is nothing but called charging current. When we are charging the capacitor, then the electrons from the positive plate of the capacitor start flowing towards the positive terminal of the source. As soon as switch is closed, we have to take into consideration three important things. First one, the potential difference between the plates increases gradually. Point number two, charging current gradually decreases. And the third point, charging of capacitor stops as soon as the potential difference between the plates of capacitor becomes equal to supply voltage. When we charge a capacitor, some work has to be done. This work is stored in the form of electrostatic potential energy. Let Q equals to charge on the plate of capacitor, C equals to capacitance, and V equals to potential difference between the plates of capacitor. Now suppose we transfer extra charge dq to capacitor, then also work has to be done. The work done in storing extra charge dq, this work done is stored in form of electrostatic potential energy. So electrostatic potential energy du equals to the amount of work done is equals to product of V and dq. But V equals to Q upon C. Therefore, du equals to Q upon C multiplied by dq. Let Q equals to 0 be the charge on capacitor at beginning, and Q equals to capital Q be the charge on capacitor at end. So capital Q is nothing but total charge stored in capacitor, and to store this charge work has to be done, and that work is stored in the form of electrostatic potential energy. Now to find total energy U, to find the total energy U, we must integrate du. So U equals to integration of du and integration of Q upon C dq, and the limits of integration from 0 to Q. Now 1 upon C taken outside, integration 0 to q dq equals to 1 upon C. Integration of q raised to 1 is nothing but q raised to 1 plus 1 upon 1 plus 1, and the limits are 0 to q. This is equals to 1 upon C q square upon 2, and limits are 0 to q. Now 2 is taken outside, so 1 upon 2c. Now applying limits here, so q square minus 0. So that is equals to half q square upon c. Therefore u equals to half q square upon c. U nothing but total energy stored in charging the capacitor. Total energy stored in charging capacitor. And we can also express energy stored in the capacitor in different forms. Case 1, we know that Q equals to CV. Therefore, U equals to half. In place of Q, you can write CV. So Q square upon C, that is CV whole square upon C, equals to half C square V square upon C, equals to half CV square. Therefore, another formula for energy stored in capacitor, U equals to half CV square. Case 2, we have C equals to Q upon V. Therefore, U equals to half Q square, and in place of C we can write Q upon V. This is equals to half Q square upon Q multiplied by V. So U equals to half Q V. So these are the different formulae for energy stored in a capacitor. Now let us consider series and parallel combination of capacitor. So we need to find total energy stored in series combination of capacitor as well as total energy stored in parallel combination of capacitors. For that, let us consider U1, U2, U3 and so on Un be the energy stored in individual capacitors. Let Cs be the equivalent capacitance of series combination. So 1 upon Cs equals to 1 upon C1 plus 1 upon C2 and so on plus 1 upon Cn. The energy stored in a capacitor U equals to half Q square upon C, which can be written as half Q square into 1 upon C. Now 1 upon C here we can take as a 1 upon Cs, that is the equivalent capacitance in series combination. Therefore, 1 upon Cs can be replaced by 1 upon C1 plus 1 upon C2 plus and so on plus 1 upon Cn. Now, opening the bracket, half Q square upon C1 plus half Q square upon C2 and so on plus half Q square upon Cn. But half Q square upon C1 is nothing but energy stored in the first capacitor, call it as a U1, and half Q2 square upon C2, call it energy stored in the second capacitor, denoted by U2, and so on. Half Q square upon Cn is nothing but energy stored in the last capacitor, that is the nth capacitor. We can denote it by Un. Therefore, U equals to U1 plus U2 plus U3 and so on up to the Un. Therefore, from above calculation, it is clear that in series combination of capacitors, total energy stored equals to sum of energy stored in each capacitor. And in case of parallel combination, equivalent capacitance Cp equals to C1 plus C2 plus C3 and so on plus Cn. And we know that energy stored in case of single capacitor is given by half Cv square. And for parallel combination, parallel combination, U equivalent equals to half into Cp into V square. So half, what is the Cp value? Cp value nothing but C1 plus C2 plus C3 and so on plus Cn multiplied by V square. Now we'll open the bracket, we get half C1 V square plus half C2 V square plus half C3 V square and so on plus half Cn V square. But half C1 V square is nothing but energy stored in first capacitor and half C2 V square energy stored in second capacitor, half C3 V square energy stored in third capacitor and half Cn V square energy stored in nth capacitor. So U1 energy stored in first capacitor, U2 energy stored in second capacitor, U3 energy stored in third capacitor and so on. U1 energy is stored in the last, that is the nth capacitor. Therefore, total energy stored in parallel combination of capacitor, we can call it as a U equals to U1 plus U2 plus U3 and so on plus Un. Therefore, in parallel combination of capacitors, total energy stored equals to sum of energy stored in each capacitor. Thus, total energy stored in series and parallel combination is same, that is U equals to U1 plus U2 plus U3 and so on plus Un, and total energy stored is equals to sum of energy stored in individual capacitor.